Hello everybody, and welcome to this Tech Week webinar on how artificial intelligence could make New Zealand roads safer. Just a little bit about the format of the session today and some housekeeping first of all. We've got you all muted at the moment, probably best to stay that way and communicate in the chat window if you do need to get our attention for anything. Just letting you know we are recording this session today and we'll make it available afterwards as well. I'll shortly introduce Adam, who will present what he's been looking at in this area. He's going to take you through the webinar. The main content will take about 15 minutes, and then we'll take any questions at the end. Again, we'll do that through the Zoom chat area. So if you have any questions, please feel free to type them in there at any time. I'll collate those and interrogate Adam with them at the end of the session. As for me, I'm Dave Sanders. I'm Managing Director and Co-founder of Intranel. We're a software development and consulting company based out of Christchurch. We've been working in a wide range of areas and industries over the years, but first dabbled in machine learning and neural networks way back around 2002, when we were looking at image recognition for a video security system we were working on at the time. We've got back into artificial intelligence more recently, and things have certainly changed since the good old days. What used to require significant computing power to get you anywhere really can now be done much more effectively, even with small embedded hardware devices such as a Raspberry Pi along with a Google Coral accelerator device for around 300 New Zealand dollars. This has opened up the ability to use AI in ways that were never even possible even a couple of years ago, as processing can now be done in situ instead of having to send streams through to data centers and waiting for processing there. So Adam Lyness, he's been leading our AI sector of the business here at Intranel, and one of the things he's been very interested in is its potential for improvements to road safety. He's also a co-founder of Intranel and an all-round excellent person to talk to about anything tech-wise. I'll hand over to him to take us through the talk, and please remember any questions, send them through to the chat area and we'll get to as many of those as we can in the time available. Adam, over to you.
Yeah, hi everyone, and thanks Dave. As Dave mentioned, we've been building our AI capability, especially in that computer vision space, developing tools to recognize and track pretty much any object using hardware like Google's Coral accelerator. And this has led to conversations on where AI could have the biggest impact in New Zealand. And road safety really is coming out to be a clear winner in that space. So I'm just going to dive straight into it here. Today, I'm arguing that an affordable, effective, and politically tenable AI-driven road safety network is both viable and could save a lot of lives and serious injuries. So this type of smart safety net requires expanding our view of road safety beyond just physical infrastructure and incorporating more high tech in that mix. So with current technology, we see this as an engineering challenge with manageable risks and not blue sky research. So I guess we've all read about the space race to build autonomous vehicles. Again, very exciting, but it's probably a 20 to 30 year time frame to fully replace our existing fleets. And that translates to a lot of ongoing road carnage. So while a lot of work is also occurring in the intelligent transport sector, there hasn't really been a razor sharp focus on optimizing safety at scale. And we think this gap could be addressed comprehensively within about 5 years with relatively cheap, proven AI and IoT technologies to reduce accident harm. So to illustrate this, I'll outline a concept system that could be cost effectively retrofitted to our road network and vehicle fleet. So at stake here, we have human lives, and the road toll in New Zealand, it's remained fairly static despite many campaigns around driver behaviour. These are expensive and slow to shift the needle because the major underlying factor we're up against is human fallibility. So, anecdotally, when I talk to friends, just about everyone, including myself, admits to having made a mistake that could have seriously hurt someone when driving. And the social cost of this is huge, estimated at about 4.8 billion in 2017 across 378 fatalities and about 3,000 serious injuries. And that's NZTA modelling, these figures come from. So when we look at fatality rates, New Zealand fares poorly. You can see Australia highlighted there at 5 deaths per 100K. Well, we're coming in quite a lot further down the OECD table at about 7.9. And these higher accident rates are driven by New Zealand's high-risk roads, our extensive network of 2-lane highways without centre barriers, and an older vehicle fleet. And this makes a stronger case for AI-based safety infrastructure, as it has the potential to be more effective here than potentially many other places. So AI is super valuable for a distributed road safety network, as I guess on a fundamental level, you need to know the location and velocity of moving objects on the road, plus the topology of the road itself. And it turns out that the latest generation of AI tech is really good at tracking multiple objects reliably and cheaply on low cost, low power hardware without needing a cloud connection. If you then communicate that data to an in-vehicle module that can assess risks and provide drivers advance warning to avoid accidents before they happen. If we look at earlier computer vision techniques, they tended to struggle with variations in lighting, orientation and background. But current algorithms are vastly better and enable plug-and-play nodes to be added to a network where required without having to do complex tuning. AI-powered smart cameras are also a lot cheaper than radar and LiDAR technologies. You can see this reflected actually in Tesla's approach to driver assistance features, which are primarily camera-based. AI can also be used by in-vehicle modules to detect a sleepy or distracted driver, again, both major causes of accidents. And this is no longer a major technical stretch. All this can run on cheap hardware, providing older vehicles many of the key safety benefits of high-end newer vehicles. We're also seeing the convergence of other technologies helpful to building a network. So this would include IoT technology, solar, battery and communications tech. Now, all of these are mature enough that implementation and deployment risks are well understood. So just a couple of screen grabs here, just to serve as a few illustrations. This is a project we did to track and differentiate different brands of scooters. In this case, it's a Lime and Flamingo. So as Dave covered before, this is running on $200 worth of hardware. In this case, a Raspberry Pi and a Google Coral inference engine, and that's running at real-time video frame rates. So training the model to recognize scooter brands only took a few hours. And we can get increasingly complex scenes trained to recognize more models. So this one's an open source tracking project showing a complex scene. If you look up there with the persons circled there, it's also a good example of AI not being infallible. So if that person on the side of the bus, as far as the AI is concerned, it is actually a person stuck to the back of the bus, as the AI is unable to take account of broader context in the way a human brain does. And this is actually one of the reasons why it's very difficult to make bulletproof autonomous vehicle systems, something I'll touch on next. So in talking about a road safety network, it does raise the question of why we need smarter roads if we can just wait for smarter cars. If we're meaning fully autonomous vehicles, the challenge is we may be waiting 30 years in New Zealand before that really becomes ubiquitous and the existing fleet is replaced. So that equates to 10,000 deaths and maybe hundreds of thousands of injuries. Another problem with AVs is that reliable autonomous vehicles are orders of magnitude more difficult to achieve than a supplementary safety network, as the acceptable failure rate is close to zero. Most of us aren't going to embrace computers that occasionally glitch and kill people. A supplementary safety system doesn't need to be right all the time to deliver on its core purpose. In fact, it may even be better not to be always on to deal with human factors, preventing over-reliance or complacency when people are driving. Smarter cars, of course, also encompasses newer vehicles equipped with advanced safety features, including collision avoidance systems and automated braking. And of course, while these systems are limited by sensor capability and connectivity in the sense they can't see around corners or talk to a network, they're already saving lives, which strengthens the case for looking at retrofitting existing vehicles. We think a safety network that tracks everything on the road represents the gold standard, as it doesn't require modules in every vehicle to work and encompasses vulnerable road users like cyclists and pedestrians from day one. It's also highly complementary to autonomous vehicle tech and other in-vehicle systems, providing an additional reference point to combine with other sensor data. So it's going to boost safety and reliability of virtually any other system. And in Just talking about government involvement in general, what we're seeing is that they're tending to leave high-tech road safety to vehicle manufacturers, which isn't ideal. We believe government is the major funder of infrastructure, has a role to play in collaborating on high-tech roading infrastructure and supporting development of protocols and standards around this. So here's a basic topology of how we think intelligent road safety infrastructure might work. This system's focused on safety rather than automation or traffic management, but obviously it would complement those functions strongly too. So the core of the system is based around roadside tracking nodes that know their location in relation to the road and can collaboratively track location and velocity of vehicles, pedestrians, cyclists, and other objects within visual range. It's probably a good point to raise a challenge that we do get around potentially lighter weight solutions, for instance, combining high accuracy in-vehicle GPS with vehicle-to-vehicle communications to try and avoid the need for roadside nodes and infrastructure. Yes, absolutely, that has merit, and it may be a good starting point, but it does require a very high percentage of drivers to opt in order to be effective. And we believe that there's fundamental benefits around performance and uptake and integrating tracking into the road network itself and exposing API interfaces that any equipment can access. So if we zoom into the roadside node here, you've got familiar tech, your road-facing camera, an AI engine, GPS module, mesh wireless connection, and a couple of redundant powered Ethernet connections to two separate base stations. The roadside nodes also work together to hand over tracking vectors for individual vehicles to get better location and velocity estimates and minimize the effects of occlusion from other vehicles. Base stations are spaced every 1 kilometre, and these would power a 500-metre string of 10 nodes in either direction. These could draw power either from the grid or a solar battery combination. Cloud connectivity, again through 4G, 5G, a LoRa IoT connection, trunk radio, satellite internet, loads of options there. Wireless connections can be low bandwidth, given that your AI and your image processing is occurring in local hardware. Although high bandwidth connections through 5G do open up a lot of additional possibilities. In-vehicle modules also are important to get data back to the driver. So these receive data from the road network and they calculate potential risks to the driver. If these exceed a threshold, you've got several tiers of audio and visual alerts depending on the risk level. Now that in-vehicle module can also act as a black box recorder with both accelerometers and road and driver-facing cameras. So these can generate alerts around driver fatigue or distractions. And driving data leading up to near misses or accidents can also be used to improve risk models and interventions. More on this later. Your nodes are designed to be modular and redundant. They can self-adapt to their location, which means a roading crew can drop in a replacement as easily as they could replace something else simple like a reflector post. So once we've got a road safety network in place, the question becomes, how does this actually reduce accidents? Well, the AI's job is to give drivers advanced warning of hazards, whether they originate from the driver's behaviour or another vehicle or a hazard on the road. So the right of the table here shows some of the major causative factors summarised from NZTA's crash accident system. If we compare them with AI detectable events on the left of the table, intuitively, it's not difficult to see how this could start to have an impact on improving safety. So heuristics around risk alerts can be fairly simple. For instance, if you pull out to overtake and there's an oncoming vehicle, you'll get a warning. Metrics around what constitutes dangerous driving are more complex and could involve a combination of conditions, speed and acceleration, crossing the centre line, or even risk models built using machine learning drawn from data recorded prior to other near misses or accidents. In a comprehensive safety network, of course, messages can also be micro-targeted to a particular area. For instance, if an accident's blocked a road, Or if police have initiated a pursuit, say, of a dangerous driver, you can actually warn drivers in that vicinity to get off the road to reduce risks from that fleeing driver. And of course, any safety warning system comes with behavioural challenges. If users feel overwhelmed with unnecessary warnings, they get sick of them and they're going to pull the plug. So, you know, I guess an example is that annoying beeping in Japanese imports. If you travelled over 100 kilometres an hour or 110 Ks, that pretty much everyone disconnected. The good news, I guess, is that AI can substantially mitigate some of these human factor challenges, and that it recognises and adapts to different drivers and driving styles when assessing risk. As an example, if it knows you typically drive up to an intersection at a great rate of knots before slamming on the anchors, it can adjust when it warns you appropriately. Again, this is just bouncing back to the crash analysis system data. So you can see around Christchurch, there's a lot of records for type, location and severity of accidents, as well as causative factors. So a huge benefit of a road safety tracking network is that even on a small scale, it yields comprehensive data, not just on the lead up to accidents, but also near misses, which currently get missed and probably outnumber accidents 10 to 1. This could include accelerometer, positioning, and driver attention metrics, all measurable between the network and a basic in-vehicle module. And this driving data provides valuable statistics and can be used to continuously train AI and risk models, enabling better targeting of risky behaviours. This means that interventions can be much more nuanced than, say, instantaneous speed cameras, and can have an educated focus with personalised feedback available to drivers. I've actually got a little picture there of one of E-Road's devices that they're producing in New Zealand, and these provide feedback to professional drivers already, and anecdotally this is leading to self-correction and safer practices. And for data at the policy level, well, strong data enables better safety interventions and a better return on infrastructure investment. So I guess with systems like this that track things, then you're always going to have privacy concerns that you need to address. Many would argue that driving is a privilege and that drivers don't necessarily have a right for their behaviour to be outside the purview of the state. And I think there's perhaps some tacit acceptance of this with wide deployment of enforcement measures already in traffic cameras that in many urban locations are already tracking vehicles around central city areas. Privacy is manageable with system design, and the AI processes happen on local nodes, and video data certainly isn't routinely sent to a central server. And I guess from a privacy perspective, there's a huge difference, say, between hoovering up every license plate and centralizing it versus local roadside nodes receiving a list of stolen vehicle plates and just looking out for those. So vehicle or video data would only be centralized in the event of a serious accident, as would in-vehicle module data. And I guess this is similar to the situation now where drivers installing cameras for their own peace of mind. So politically, we wouldn't see more advanced road safety systems causing major public backlash, particularly if initiatives are community-led and the core focus on saving lives was maintained. The threshold for non-anonymized reporting of risky or illegal driving behaviour is something that should be negotiated with communities to ensure buy-in is present, and probably human review applied to reports prior to sanctions being applied. You wouldn't want to end up with a dystopian kind of future where it automatically starts deducting $1 every minute from your bank account for every K over the speed limit. Talking about uptake, we could certainly see initial appeal to the insurance industry, parents of young drivers, people living in areas with high accident rates where it's already a topic of widespread discussion. And talking about how we'd get this off the ground, well, given sufficient seed capital, we would apply a lean business approach to kickstart a network, focusing effort where it could have the biggest impact. So this could be a rural town or maybe a high-risk, well-trafficked route where we could get community buy-in and a high degree of coverage, say, for users on their daily commute. Given time, your prototype can collect hard data on risk factors, accident rates, near misses, and as well as impact of safety interventions. If you've got strong data and a reduction in accidents, this is going to support further investment, and the system can be extended to save more lives. For looking at costing, it's obviously very preliminary, but the basic modelling we've done suggests a return on investment of over 600% on capital, assuming a 15-year lifespan and using NZTA's own model for costs of social harm from accidents. Your installation and your ongoing costs would probably represent less than 5% of current per kilometre costs of state highway. So really it's a relatively modest expense, given that we think you could get a reduction of at least 35% in fatal and serious accidents. We think there's a role for government to fund non-physical infrastructure and collaborate around innovation and deployment of standards in this space. So that's it for the main part of the presentation. Just recapping, we think that smart road safety networks are worth exploring independently in New Zealand, as we're particularly well placed to benefit, and really a lot of the rest of the world is distracted with that space race to build autonomous vehicles. There's a 20 to 30 year gap before AVs become ubiquitous, and a lot of lives could be saved in the interim with strategic application of new technologies. So the core technologies to build an effective safety network are relatively mature. So the problem, as we see it, is an engineering one with managed risks rather than blue sky research. This stuff is viable now and it's affordable. So at this stage, we're developing the concept, having a number of conversations with tech and transport people. And it looks like there's several interested parties in a potential consortium already. So, please hit me up if it's something you'd be keen to be involved with, or if there's someone we should talk to. Also, obviously, good to hear your thoughts on anything I've got wrong or missed. So, look, that's it from me for the formal part of the presentation. I think Dave's probably collected a few comments and questions from the session, which he's going to fire at me now.
Okay, we've got a question from Matt Ensor. Are there things about New Zealand that make it a good test bed for this?
Yeah, I would say yes. I mean, we already covered why the potential benefits in New Zealand are more than places with maybe more developed state highways, in the sense that we've got a relatively extensive and currently high risk vehicle network. I also think there's a good track record of experimenting with and trying out new technologies within New Zealand. I think the uptake and the preparedness to do that's quite high. We see that with a lot of new technologies being deployed in New Zealand.
Well, thanks. Question from Stefan. What would the prototype proof of concept actually look like?
Well, you've got a couple of different directions you could go in there. My view is building a more comprehensive road-based network in a smaller area. So, you could take a town like say the size of Wanaka, where you've potentially got a relatively high impact from accidents around the area, particularly in tourist season when that was a thing. And you could focus your infrastructure around on the state highways around there. Do that at moderate cost. So you want it to be small enough that it's affordable for the risk you're taking, but big enough that you're going to get statistically significant data out of it that can justify further investment. Also operating on a small scale, you can start to have long, local conversations, and getting that high level of local buy-in is going to be really important for something like this. If you look at the international space, there's a lot of proof of concepts and portions of this technology that have been trialed in professional vehicles and so on. But what we haven't seen is really anyone doing this at scale, or certainly if they haven't made the data sets publicly available yet.
Right. Thank you. What proportion of vehicles would need to have the system installed and to make it viable? And another follow-up question to that, what would the cost per vehicle be for that vehicle installed as well?
Yeah, when we do a breakdown for an in-vehicle module, just looking at a basic BOM for the key components. So again, they're all commodity equipment, so they're relatively inexpensive. So our estimate is under $350 a vehicle, including about $100 for basic installation for a dashboard module. So that's an estimate, but it's going to be somewhere within that vicinity.
And how many would need to? How many vehicles would you need to have that in like a proportion basis to make it viable?
Yeah, so one advantage with building roadside infrastructure, it means that any driver that opts into the program gets all the benefits of a network that can track all your other vehicles. Whereas if you go with a vehicle-to-vehicle approach, obviously you only get network effects when you've got a very high proportion of vehicles with those installed. So, again, if you can cover a smallest geographic area, but it covers most of the travel people in that area do, you can start to get, the system becomes useful and viable for every driver that installs that system without.
Right. So you're essentially saying there's some benefits that you get from the roadside system for any vehicle that's got it installed, but then there's further benefits you get depending on the proportion of people that have got it after that.
Correct.
Is that fair? Yeah.
Correct. And to prove out this technology again, I just emphasise that focusing on a small geographic area for a test bed would be the way to go and try and get a high level of community buy-in.
Cool. There's a question from Richard here about the estimated total cost to the government to install roadside tracking on all New Zealand roads. But that also ties in with a question I had for you as well, which was, you mentioned an estimated 35% possible reduction in fatal accidents. Mm-hmm. So how much road coverage would you need to see that kind of reduction? Is that based on all road coverage or major roads? What's the situation there?
Yeah, so I think in most cases you'd focus your initial deployment on areas where you're going to get the most benefit. So if you look at the social cost of accidents per kilometre, tends to be state highways, areas of rural roads, outside the urban areas that are most dangerous and would benefit most from this technology. The figure of 35% comes from some of the data we already have for more sophisticated in-vehicle safety systems, which indicate those kind of reductions in serious accidents already. And the system we're talking about deploying would actually offer far superior interventions to what's available there as well. So it's a reasonably conservative figure.
And have you estimated, or can you estimate, the total cost to the government to install the roadside tracking on all major New Zealand roads, or all deemed at-risk roads, I guess?
Yeah, well, I guess you need two things to happen. First of all, you need wide coverage of your vehicle network on a nationwide level, and you need in-vehicle modules for individual drivers to benefit from that. So the cost to cover the whole state highway network plus all your getting a module in every vehicle, you're looking at something in the order of just over $2 billion with our rough modelling. So it's a significant sum of money, but there are ways you can spread that cost. And as I say, you would never spend that kind of money until you've done smaller pilots and you've got clear data that indicates it would be a worthwhile investment.
Right. Question here, I'm not sure if we're at this stage yet, but how would vehicle owners that want to participate get access to the hardware, and who would pay for the hardware and installation costs?
Yeah, well, this is an interesting one. So it depends on what kind of consortium you build and who the partners are within that, how some sort of pilot would be funded. So you could certainly see, in the insurance industry potentially sponsoring some of this work. If you can build the right consortium, you can start to get the attention of government. There's potentially some funding avenues there, and obviously if there's obvious benefits to drivers participating as well, you could ask them to make a contribution too. So I mean, your cost models, how you launch a system once you've built the technology, I think they tend to resolve pretty quickly. Obviously before you can even get there, you've got an initial sort of R&D process to build and prove out, do some of the engineering on a smaller scale. which is something we'd certainly need to focus on first. But I can only emphasise again that this is an engineering problem plugging into existing technologies together. It is a complex system, but it's certainly something that could be achieved quite quickly.
Cool. Question from Maria here. You mentioned tracking of scooters in the presentation. How flexible is that particular tool to track and learn from less traditional transportation methods, such as, well, it says scooter, walk, cycling, etc.?
Yeah, very flexible. So it's actually pretty quick with modern tools to train AI models in a variety of contexts to pick up virtually any mode of transport that you want to track. So if that's pedestrians, people on scooters, people on bikes, whether they be regular or recumbent, you can build a fairly comprehensive list and identify and classify and track all of those. So one nice thing about the system, of course, is you're not just you can anonymize and collect that data and feed into other aspects of policy outside of the safety space.
Following up on that same question, how easy would it be to integrate that with crowd modelling software, for example, for better understanding how the road network behaves during an extreme event, such as evacuation events from disasters and climate events, earthquakes, things like that? I actually know this will be the road safety system. So integrating that with other cloud modelling software.
Well, I mean, ultimately, if you're continuously tracking every moving object on large portions of your transport network, I mean that's a huge amount of data. So if you can anonymize and store that data using 5G technologies to get that centralized, you've got a very powerful, you've got a huge data set which you can start to apply powerful tools for doing a bunch of predictive analytics or having a very good understanding of the impacts of natural disasters or high impact events on traffic flows and challenges.
Right, so the data's there, it's just a matter of doing other processing on that data.
All there, right? At a raw level, the system's collecting everything. So how you anonymize and distribute that and what you do with it, again, that you've just got to identify the value propositions there, and it's going to be available for doing all kinds of things.
Question from Andy. What considerations have been made for installation of new infrastructure alongside existing roadside infrastructure that's already in the road corridor, such as fibre and electricity?
That's something I don't know a lot about. I mean, we have had conversations with a few people in the roading space. As far as I'm aware, new technologies like this, there is scope and regulatory pathways for piloting and testing things. And in terms of exact policy frameworks for how complex systems like this would be installed, I'm honestly not sure what's in place at the moment.
Yeah, there might be some other people on this call that could be able to answer that better. Feel free to put a response to that in the chat if anybody can answer that one. Next, from Richard. The question is whether the countermeasures via the driver after hearing warnings from the in-vehicle module. So does it all go through the driver essentially? And what does that mean in terms of delays and drivers being advised of hazards, imminent crashes, etc.?
Sorry, just with that.
So does that make sense?
Maybe just repeat that again. So
so are the countermeasures via the driver hearing warnings from the in-vehicle module? And if so, what's the impact of that on, I guess, delays and the drivers being advised of hazards, distracted from those by the in-car module?
Yeah. There's a number of ergonomic approaches, I guess, you could take to this, and getting that right is actually probably one of the bigger challenges in this system. And it's certainly a problem in existing in-vehicle warning systems, and that if you have something that continuously beeps every time it sees a cyclist that the driver's already seen, you risk a bit of attention fatigue there. So it's certainly a challenge getting that right. To me, it's like you have an escalating scale of warning. So a little bit of audio and visual stuff. So, you know, for instance, if you're on an open road, you're coming around a corner, there's a cyclist, they're traveling relatively slow. It would just be a fairly nuanced little flash a couple of times, and probably a little picture of a cyclist on the screen of the dashboard based device. If you were coming up to a stop sign and you clearly weren't slowing at a safe rate, you're going to get a pretty loud, pretty attention-grabbing warning to give you a chance to at least mitigate or avoid going through that stop sign at high speed. So, you know.
Yeah, I certainly understand the problem with that. When my car has a warning when it thinks I'm going to crash into something, it beeps at me and it says brake on the dash. And if anything, it's distracting because it's just a beep. You go, what's that beep? And you look down to see what it is, and it says brake. So it's actually more distracting than anything else. So I think, yeah, getting that right is quite critical.
Yeah. And as I say, we covered that in the presentation. One of the advantages with AI is the ability to actually learn your driving style. So right. The system itself, as far as it's concerned, you're a good driver. Most of the time it doesn't need to tell you every time you're coming to an intersection, and it won't. Where it does intervene, in that case is where you're not slowing within the normal envelope of safety.
Yeah, good question here. Will phone technology get to the point where your phone can actually be the in-car device rather than having to have a specific unit?
Yeah, my view on that is the costs of actually producing an in-vehicle device with a little dash-mounted display are so low that there's not a hell of a lot of benefit to using your phone. As you can imagine, if every time you get into your car, you have to sort of take your phone out and plug it in so it doesn't go flat if you're doing a long journey in the open road, and pop it in a mount and so on. It's if you want this type of system to be ubiquitous and just part of driving eventually, you don't want to create that extra hassle and step of having to faff around with your own device. Having said that, if you're looking at prototype systems, building and testing some proof of concept technology, then being able to leverage your phone can be quite useful.
Quick question here. What's the estimated spacing of the roadside nodes that you're talking about?
Well, we talked about every 50 meters, but I mean that's arbitrary. It's the kind of thing you'd need to do some testing with the cameras and so on, just to look at sort of what the optimal level of spacing is to be able to have reasonable tracking. And obviously, the gold standard is continuous tracking of vehicles. If you can do that, then you can start to assess whether someone's sort of swerving all over the road, taking corners too fast, crossing the centre line, and so on. And one of the key things about this system is to be able to provide feedback on your own driving, or to warn other drivers, oncoming drivers, that there's a reckless vehicle approaching, or a vehicle on the wrong side of the road, and so on. And that's a significant risk mitigator if you can give drivers fair warning if someone else is driving dangerously.
Question here from Michael. Have you considered environmental benefits or potential environmental benefits such as reduced emissions in this system at all?
Well, I think some of, again, with the tracking network, you've got the data there to potentially look at optimizations around traffic routing, vehicle spacing, and journeys, right? And when we talk about smart roads and intelligent transport systems in general, this is where it's heading over time. This concept that you can sort of virtualize the convoys of vehicles or packets of vehicles and so on, and manage flow through intersections by managing the spacing with fully or partially automated systems. So the focus we're taking is saying, okay, short term, the biggest benefits are if you've got a real safety focus, but it's certainly a step along the way to being able to create more efficient networks and fleets, and that's going to have significant environmental impacts over time as well.
And just following on from that one while we're kind of on it, what form of interventions would there be for only roadside nodes with no in-car units? Would you still be able to get things like variable speed limits and warning signs, or just identifying problem areas which may need physical improvements?
Yeah, I mean that's a good point. There's if a vehicle doesn't have a an in-vehicle module, you've got roadside units. They can have visible warnings for drivers approaching intersections, or or they could flash urgent codes if there was sort of a major upcoming hazard. So yes, even without an in-vehicle module, there are ways of communicating potential hazards or risks to drivers. So it's certainly worth giving it some consideration.
Cool. Just backing up to a question from Andy, how sensitive would the roadside network be to movement? Would it pick up animal movement, for example?
Yeah, well, an animal or stock on the road, again, it's just another object that you'd almost certainly train the network to recognise, so that just becomes an identifiable hazard on the road that where you could warn approaching drivers that there is cattle on the road, particularly if that cattle is in an area that could be hard to see.
And last question at the moment, back to estimated cost. So using the 50-metre spacing on both sides of the road as an example, can you give an estimated cost to the government of installing the roadside roads on all New Zealand roads at that kind of spacing?
Okay, what have I got here? I think looking at the costs I've got here, it was mostly modelling that we did focused on state highways, so approaching the roads where, because of the less complex visual environment, it's probably going to be easiest to do. And that figure, when you looked at sort of equipping sort of all the 3.6 odd million vehicles in New Zealand with an in-vehicle module plus state highways, you were looking at sort of just over 2 billion odd cost. If you started, what's
the split there between the roadside nodes and the in-vehicle?
It's actually, if you looked at all the state highways, the slightly higher cost is actually the in-vehicle module cost. Over time, your in-vehicle modules obviously don't incur an annual maintenance cost as well in the modelling, so that's a little bit different. So the answer to that is probably in the region of about $3.5 to $4.5 billion to really deploy something like this across the whole country. Now you may get some that may come down because at that level you're obviously getting some pretty major economies of scale.
Excellent. Okay, that's the last question I can see in there. Last chance for anybody, but that has any other questions. But otherwise, thanks to everybody for coming along. If you do have any further questions, oh, there's one. Would urban areas be very much more expensive to cover than open roads?
It's a good question. I would say, given the number of intersections and so on, you'd probably need a higher density of cameras in some areas. I think it would be broadly similar. It's a more complex visual environment. Again,
so the processing and software costs could actually be harder, I guess, in the urban area rather than the installation cost.
Yeah. So within an urban space, for instance, you've got you're traveling at slower speeds and you've got a high number of risk factors coming out at you at all times. So so you don't want to know every time it sees a cyclist or a pedestrian who looks like they might be about to start crossing the road. So within urban areas, it's like the systems become a little bit more powerful if you can link them up to automated braking systems and so on, which are appearing in newer vehicles, because then you get the benefit of a vehicle that can not just detect a hazard but actually react faster than a human can and do that for you.
Yep. A couple of last quick questions coming through from Carl. I imagine labour to install and service would be the higher cost component. Do you have any indication of who might provide that installation and servicing over time?
Yeah, well, we in our basic modelling, we assume sort of an annual maintenance and costs for the network of roughly about 7.5% of the total initial capital cost of the network. You know, I think if you can design them, the modules appropriately, to make them very much plug and play or drop in replacements. If there's damage to a network, it's going to be pretty quick to train your existing roading contractors to be able to maintain.
Just swap them out rather than,
as well.
yeah.
Correct. Yeah.
So
avoid the need of having to tune units when they're plugged in.
Yeah. So what would be the estimated cost per installed roadside node, including a power supply to that?
Yeah, we're having it. What node cost? So roughly, you know, we think it's going to be that in that sort of, you know, $1,000 to $1,200 cost when we sort of do a breakdown and looking at the hardware that we think you'd need in there. So the roadside nodes are designed to be, you know, as minimal as possible, but as a, you know, again, the hardware in those is you know, very much commodity type stuff now. Your base stations are going to be a little bit more expensive, probably at your 5K cost. And some of this depends on, you know, what kind of infrastructure, you know, you want to include. If you're saying, right, this is a great opportunity to get sort of a big 5G network deployed all along your state highways, then that equipment could, you know, add to some of that cost, but obviously has other benefits and potentially connecting all your vehicles to you know, broadband internet as well.
Right. And I'm going to make the last question call on this one. It's a good one. What do you need to make this happen? What are the next steps?
So I guess we've been having a few conversations with people in this space, and there's a bit of interest in the potential for putting together a consortium. We're certainly interested in talking to people about that. I mean, I think, you know, we're looking at including or approaching a few insurance companies. There's some organisations, so like Trimble within the New Zealand space, who are involved in high accuracy GPS equipment and so on, who might be a natural fit too. You know, I guess we're interested in hearing from people, anyone else we should be talking to, or anyone who's interested in being involved in this space. You know, I guess if you want to start moving something like this forward, then, you know, you need to I guess build an industry group that has some credibility, and then you can start to open up conversations with government and look at avenues to funding from various quarters.
Excellent. So you've already talked to some other organisations and things. So yeah, anybody on this call that is interested in discussing that further, yeah, get in touch. So I called last question on that one. So thanks everybody for coming along and listening. If you do have any further questions or want to talk through this or even discuss your other projects, we're happy to chat. You can reach Adam at intranel.com. I'm at david@intranel.com. We'll also send out the slide deck that Adam did today to everybody, and a link to the recording of the session once that is sorted out. So it was great to have you all along. I hope you've been enjoying the Tech Week program, and have a great afternoon.
Yeah, thanks everyone. Appreciate you coming along.